its reaction with a zirconium alloy, which might be used as cladding, and the effects of particle sizes on chemical behavior. It was found that UO2 could be sintered successfully if carried out in a hydrogen atmosphere. This process increased both density and strength. Many tests, including in-pile irradiation, were performed on uranium alloys and UO2. Included were tests on intentionally defective samples. Based on these tests, the oxide offered the most promise. Accordingly, it was selected as the blanket fuel. Although the development of the manufacturing processes was then begun, the extensive test program was continued to verify the selection of UO2. More than 2 million uranium oxide pellets and 95,000 blanket tubes were made. Processing of pellets included agglomerating, compacting, sintering, and grinding. Fuel rods and bundles were assembled, argon atmosphere welded, annealed, and machined. In the meantime, seed elements were also being made. The basic component of the seed cluster is an enriched uranium fuel plate. It is sandwiched between two zirconium alloy cover plates. Sub-assemblies were joined with the necessary spacers to create a cruciform channel for the control rod made of hafnium. Hafnium, being a good neutron absorber and having high corrosion resistance, is ideally suitable control rod material. While fuel manufacturing proceeded, extensive reactor physics calculations were performed to determine the design reactivity of the core. A certain amount of excess reactivity, to be controlled by the control rods, had to be provided to compensate for fuel depletion, for the buildup of fission product poisons, and for reactivity changes between room temperature and operating temperature. To provide for experimental checks of the calculations, a flexible critical experiment, in reality a nuclear model of the core, was constructed at the Bettis plant. It was designed to operate at room temperature. Using this critical assembly, calculations of reactivity at room temperature could be checked with reasonable precision. But the reactivity at operating temperature could be anticipated only on the basis of calculations. Initially, there must be sufficient reactivity to sustain criticality or a neutron multiplication constant of 1 or unity. The excess reactivity was designed to include 6% for fuel depletion, 4% for fission product poisons, 3% for temperature changes, and 5% for design margin to allow for the uncertainties in the design of this unprecedented type of... The total of 18% excess reactivity was selected as the optimum. More might cause difficulties with operation and shutdown, less, either no criticality or shortened life of the core. Operating measurements that have been made in the plant indicate that the reactivity calculations were substantially correct, and that the 5% design margin that was included can be used to provide additional lifetime for the core. The critical assembly also permitted an accurate determination of the control rod positions required to bring criticality. It was important that this be determined because in a power reactor, unlike an experimental reactor, the technique of adding fuel as a means of slowly approaching criticality is not practical. The preliminary experimental work done made it possible to predict the initial critical position of the control rods to within a fraction inch out of a total motion of 6 feet. The critical assembly also permitted measurements of neutron flux distribution. Since such measurements could be made only at room temperature, the ultimate check could be made only on the shipping port reactor under operating conditions. To permit such measurements, and thereby provide valuable information for use in the design of future reactors, an elaborate system of coolant flow and temperature instrumentation was provided at shipping port. Half of the seed and about 1/6 of the blanket fuel assemblies are instrumented for flow measurement. Approximately 2/3 of the seed and 1/4 of the blanket assemblies have thermocouples placed to measure the temperature of the water leaving the fuel assembly. Additional thermocouples at the bottom of the core give core inlet water temperatures. The temperature data and the flow data are used to compute power distribution in various regions of the core. Measurements which have been made indicate a good agreement with the physics calculations. To raise the power lever, the control rods until the desired power is attained. Then they are moved back to the operating position. To lower the output, the opposite action is taken. No action is necessary to account for changes in electrical power demand imposed on this plant by the utility network. This is due to the large negative temperature coefficient of reactivity, which maintains a constant average water temperature in the primary circuit regardless of changes in steam demand. For example, if the inlet water temperature is 508 degrees Fahrenheit and the outlet temperature is 538 degrees, the average water temperature is 523 degrees. With increased steam demand caused by an increase in electrical output, the inlet water temperature may drop to 500 degrees. The reactor automatically increases power output, and the outlet temperature automatically increases to 546 degrees. Note that the average temperature remained constant, making the reactor plant virtually self-regulating. The value of this temperature coefficient was found to be -3 × 10 to the -4 per Fahrenheit degree at operating temperature, a value which agrees well with the calculations of this quantity. Nearly 2 years of design, development, and engineering were necessary before plans began to be definite and construction drawings made up. Then, in March of 1955, construction began with the clearing of the site. By mid-1956, considerable progress had been made. The force of construction workers numbered in the hundreds. By then, a large part of the concrete shielding had been poured. The container chambers were in place, and the canal section could be identified easily. With the reactor sphere in position, major equipment items began to arrive on the site. The 150-ton pressure vessel, having completed all of the shop processes involved in its fabrication, began its journey to shipping port. It was installed on October 10th, 1956. The basic methods employed for installing the units were similar to those followed in major construction projects. A high order of cleanliness was necessary while the primary system was open, such as during installation of the thermal shield. The climax of these operations came on October 6th, 1957, the precise placement of the fuel core in the reactor. The shipping port plant has a large number of newly developed items of equipment to ensure safety and reliability. Typical of these are zero-leakage canned motor pumps. In this design, no shaft seal is necessary. Metal cans enclose both stator and rotor. Primary water circulates between them, lubricating the bearings and cooling the induction motor. A separate water supply cools the stator coils. The turbine generator is outdoors, unusual at latitude 41 degrees north in the United States. The shaft speed of the unit is 1800 RPM. It is capable of producing 100,000 kilowatts in anticipation of future core developments. The shipping port plant was completed and full power operation was begun approximately 3 years after the start of construction, which is in line with the time taken to build non-nuclear plants. The total elapsed time from the award of the design contract was 4.5 years. Control of the operation of the plant is naturally divided into 3 parts: reactor, steam generation, and power generation. In addition, extensive instrumentation will provide a vast amount of information never before available. Among the continuous readings taken are water pressures, temperatures, flow rates, and power level in the reactor. In keeping with the developmental nature of the plant, a large part of the instrumentation is provided for indicating and recording design information and unusual events, and is not necessary for normal operation. Typical of this type of instrumentation is the extensive system designed to detect and locate fuel element failures. On December 2nd, 1957, the reactor went critical for the first time. This was the 15th anniversary of self-sustaining nuclear fission in the world's first reactor at Stagg Field in Chicago. On December 18, 1957, with the generator synchronized with the Duquesne Light Company system, the first step was made to go to full power. On each successive day, the output was increased. At 50% output, the coefficient of reactivity was measured and found to be in agreement with preliminary calculations made at Bettis. The full output of 60,000 kilowatts was reached 5 days after synchronization. The city of Pittsburgh was lighted with the aid of atomic power at Shippingport. This new source of power had been put to work. It was a history-making accomplishment. Many operational tests have been conducted, and Shippingport has operated with an ease and responsiveness surpassing conventional power stations. In addition to its value as an operating power station, it is also to gain information to advance reactor technology. Tests are continuing for the purpose of carrying out this mission of the Shippingport project, to provide full-scale plant experience in development, design, construction, and operation. Experience that will be invaluable to the future of nuclear power the world over.